Okay, in this video I want to talk about the physical meaning of the heat equation. So let U, which is a function of x and t, be the temperature of a rod or a wire or anything that's really just a straight line, a single dimension, at position x and time t. Then the equation, the heat equation, is given by this. The second derivative with respect to x is equal to the derivative with respect to t. So U represents your temperature, x represents where you're at on the rod, t represents time, and then k is a constant. It's a multiple. It's sometimes called the thermal diffusivity. So the way to think about this is your temperature is going to be different at different parts of the rod. So if I'm holding the left side, then that's going to be a different temperature than the right side. If I put the right side under a fire, then suddenly it's going to heat up, and then the temperature is going to change along the rod as the heat slowly moves from right to left. So the temperature is going to depend on where on the rod you're at and also time. Something about this thermal diffusivity, this is basically measuring how well does this particular material transfer heat. So for instance, a metal rod might have a very high thermal diffusivity versus a styrofoam rod might have a very low thermal diffusivity because it's insulated. Okay, but when we have differential equations, if we're actually going to solve and get an answer, we typically have initial conditions or boundary conditions. And so these are what some boundary conditions might look like. Let's talk about what these represent or mean in terms of the picture. So this is saying that your x is equal to 0 and it's constant. So that means when x is equal to 0, that's the left side. Sorry, I had some technical difficulties there. So when x is equal to 0, that means we're talking about the left side of the rod, and u of x0 or u of xt is just going to be u0, which means it's a constant. On the other hand, if x is equal to L, so we're holding the x constant at L, that means we're on the right side and we have constant temperature. On the other hand, if the derivative of u with respect to x at x equals 0 is 0, the derivative of u, change of heat, with respect to x with respect to position would mean how is the heat moving along the rod. And if it's equal to 0 at a particular place, that means that we can't actually move heat past this particular point. So what we end up saying, how we describe that, is that, again, x equals 0 would be left side, and I'm going to say is insulated. So if you see the word insulated in any of your problems, it means your derivative with respect to x is going to be 0. Okay, same thing here, only it's the right side, because we're using x is L instead of x is 0. And this one's a little more complicated. It turns out to be some variation of something we've seen before, Newton's heat equation. Basically, I'm not going to look at many examples that look like this, but this would be if the rod is sitting inside of a medium, such as it's in water at 30 degrees. Okay, great. That's temperature of the medium. If the right side is what's in the water, then that would be an equation that looks something like this. Okay. And then the constant H is your proportionality, which could be positive or negative depending on if the heat is leaving or entering through that end of the rod. Okay, and yeah. Same thing, both of these, one of them's at x equals 0, one's at x equals Okay, so as an example, I'm going to look at this problem. A rod has length L, initial temperature f of x, and both ends are held at temperature 0. Find u of xt. Okay, so let's see. What is our differential equation? Our differential equation is the heat equation, because it's talking about a one-dimensional rod. Okay. What are our boundary conditions? let's see, both ends are held at temperature 0. So that means, let's see, looks like these top two, u of 0t is equal to 0. So at the left side, x equals 0, temperature is 0. At the right side, u equals lt is 0. And so this is x equals 0 for any t, temperature 0. X equals L for any t, temperature 0. And then the last one, initial temperature f of x. I didn't write one of those in my list of possible boundary conditions, but sure, I guess we could write it. Would be, let's see, initial temperature. That means time is 0, but the f of x is going to be my temperature. Okay, so if I hold t equals 0 and let x vary, so I'm looking at different places on the rod, all at time 0, I get f of x. So that's my initial temperature. And I guess that one's really an initial condition, and those two are boundary conditions. We'll just call them all boundary conditions.